Hello students, welcome to the first tutorial on heat measurements. Now, to introduce you to this topic, let's look at one simple description. So let's say we have what we call a heating curve. Now, I hope you guys have looked at this before. It's a concept that is taught at lower levels. But if you haven't, don't worry, you will see exactly everything that you need in order for you to work out the questions that we're going to encounter. So let's say we're dealing with a heating curve. Now, how does a heating curve look? So what we're saying is you have on the y-axis, and then on y-axis, what you have is temperature. Now, let me say this temperature is in degrees Celsius, and then on the x-axis, okay, let's just draw a line a little bit better. Okay, so on our x-axis, what we have, we can even say this is time. So this can be in minutes. Okay, solid. Let's say you start with substance. This can be ice, it can be any solid really, but it starts from somewhere here. Can we start it from the bottom? Let's say it starts from way down here. So as you are heating the substance, so this is a solid, of course you expect that the temperature will be going up with time since you're adding heat. And then until when you reach that point. And then of course something is expected to happen here. I hope you guys can recall this. And then after some time, the temperature is observed to go up again. So the temperature will go up until after some time again, it is observed that the temperature stops changing. It remains constant for some time. And then eventually the temperature again starts to go up. Now, what you guys should recall is what is happening already at the point where the temperature is not changing. So I'm going to just demarcate this so that you have certain sections that we want to evaluate or that we want to just consider what is happening with just there. And then we also have this boundary and this boundary. Now, if I was to label these points, let's say this is where you're starting from. So I can even say this is the point O, then this is the point A, B, C, D. And then that can be said to be E. Okay. Now, with that in mind, if you started with a solid, then from O to A, what you have is a solid. So let's have blue for that. So from O to A, this substance is in solid state. And then as you move from A to B, now what you're saying is, I hope you guys remember, this is a combination because what you're saying is change of state. So the substance is changing from solid to liquid. Now, next up from B to C, we're seeing a change in temperature. So apart from this, you guys should recall that what is happening between B and C is that, in terms of the state, this substance is all liquid. We'll look at what is happening in a bit of time. Okay, now from C to D, you guys should notice that the temperature is not changing. And in those boundaries, what we have in terms of state is we have a liquid that is changing to become a gas. And lastly, above D, what we see is that all the liquid has become gas, implying that now we have this substance is now in gaseous state. So we're dealing with water at negative 20 degrees Celsius. And then for water to change from negative 20 to 0 degrees Celsius, of course, water will reach the point A when the temperature is 0 degrees Celsius. So now for this temperature to increase from negative 20 to 0 degrees Celsius, the only logical explanation is that we are adding heat. So heat is being added. Now let's say the amount of heat being added here is Q. Let's say this is Q1. Now, next up, to move from A to B, here now water is from its changing state from solid becoming a liquid. And for that to happen, it doesn't mean that just because the temperature is constant, you're not adding heat. Definitely, you are adding heat here as well. And the amount of heat being added here is Q2. And from B to C, we see an increase in temperature. So of course, definitely, we are adding heat there as well. And if we're dealing with water, we know to see that the temperature will keep on going up, and it will only start changing state again when the temperature becomes 100 degrees Celsius. So the temperature, the heat that you need to add here is Q3. Now, next up, from C to D, whatever the substance is, here of course we're saying this is water. Whatever the substance is now is changing state again, but this time, as we saw earlier on, the state is changing from liquid becoming gas. And the amount of heat you need to add for that to happen is Q4. And lastly, now it is all a gas at D. Now to raise its temperature from a gas at D to whatever temperature at E, the amount of heat you need to add is Q5. Now, what we want to do, the whole purpose of this topic, or the objective of this topic, is to look at how to determine the amount of heat you need to add, let's say, to increase the temperature from -20 to 0 degrees Celsius, or just from one temperature to the other, or the amount of heat you need to remove when the change in temperature occurs. Another thing that we also want to see is how do we determine the amount of heat that you need to add to change state from one state to the other, or vice versa. So the formulas that we're going to use in the respective sections will be the same whether we're going forward or we're going backwards. Now, quickly, if we are moving from the point O to the point A, we notice that there's a change in temperature. Now, once you notice that, the formula you should remember is that we are going to use C change in T. So that's the formula that will give us what our Q is. So we're saying Q there is equal to MC change in T. So we notice that everywhere there's a change in temperature, Q will be calculated by the mass, the specific heat capacity, multiplying the change in temperature. So this will be true here as well, mass, C, change in T. And then here also, to move it from D to E, we see that here also C will be calculated by MC, change in T. Now, different materials will have different values of C. So mostly the value of C will be given to you in a question. Okay. But when it comes to the point where temperature is not changing, like the point from A to B or from C to D, to calculate the amount of heat needed to perform that change of state, the formula we use this time has to do, of course, it has to do with the mass, but now it works with the latent heat. Now, latent heat comes in two forms. See, this is change of state. If, for example, you're changing from liquid to gas, it's like you're changing from a liquid and then you're making that liquid into a vapor form. So the heat that has to do with making a vapor, this is called the latent heat of vaporization. So it's written as L with a small subscript V. And then here now, this is the heat that has to do with making this a solid. It has to do with something to do with the solid. So this is the latent heat of fusion. So this is how I remember which one I'm using and where. I know if it has to do with making a gas, it's more like I'm making a vapor. So I have LV, and then fusion is more like about making a solid. So this becomes, or it goes where we have the point LV. So of course, for change of state, wherever change of state is happening, this is how I'm calculating the heat that has to do with that. So of course, we're saying that it's either latent heat of fusion or latent heat of vaporization. So those are the two possibilities that we can work with there. Okay, now one other thing that you guys have to keep in mind is we can either move forward or we can move backwards. So if we're moving forward, then Q1, for example, here, this is the amount of heat you are adding to increase the temperature from -20 degrees Celsius to 0 degrees Celsius. This is, of course, if you're dealing with water. But if let's say you have ice at 0 degrees Celsius. And then you want to lower its temperature to -20. Then Q1 becomes the temperature, not the temperature. Q1 becomes the heat, the amount of heat that you need to remove from the ice in order for it to drop to that particular temperature. Okay, so it's the values of heat that we are calculating here. You can look at them as either the amount of heat you are adding or the substance is gaining if you're moving forward, or you can look at it as the amount of heat that is being lost or the amount of heat that you're removing if you're moving in the opposite direction. Okay, so I hope that brief description was worth something. I hope you were able to follow through. The key thing now is to see how to apply it. Now, most questions that we're going to deal with will not just depend on one substance. Mostly you're going to have two substances that are being mixed, and then you want to see how the heat amounts are fluctuating with time for each object. Now, what you have to just keep in mind is if you have two objects, let's say, I can say this is a glass, and then in this glass, you have a liquid. And then to this glass, you decide to add more of this liquid, but now at a different temperature. So you decide to add more of this liquid, but now at a different temperature. So what you guys should notice is after some time, the mixture now is going to readjust its temperature to a value such that it's more like an equilibrium, a combination of the two values of temperature, like the one you had initially in the cup, combined a little bit with the fluid that you have just added. So it's like temperature kind of readjusts to reach a point of equilibrium. So the final temperature of the two solutions, of the two liquids, is now going to be the same. So it's like one liquid that was at a higher temperature loses heat. So let's say you have the first one, let's say this is the first one. It was at, let's say 50 degrees Celsius. And then the second one, the second liquid was at, you can even say 20 degrees Celsius. And then when you combine them, the temperature that you're going to get is going to be somewhere between. So what is happening? The first one loses heat. So you can say it's more like a drop. So the temperature drops from 50, and then it drops until when it reaches this equilibrium point that you don't know. While for the second one, what is happening to it is it starts from temperature 20 degrees Celsius. So it starts from 20 degrees Celsius, and then the temperature goes up until perhaps this happens simultaneously. Once you start adding, the temperature of one starts to drop, and then the temperature of the other starts to go up. So the temperature for the second one will go up from 20 degrees Celsius until when they reach equilibrium at the same point. Now, once you reach this point, this will be their final temperature. So you notice one simple thing here. The heat lost here, so we can say the heat lost by the first one will always be equal to the heat gained by the second one. So this is the key concept that we're going to use in working out problems. Heat lost by one will be equal to the heat gained by the other. This, of course, is if two objects are either in contact or if they are mixed together. Then one loses heat, but the lost heat is then gained by the other. Of course, if there's change in temperature, heat here can be calculated by MC, change in T, and then so the same thing here, MC, change in T. So if it's the same substance, of course, C will be the same. Now there's the only question to say, is the mass that you're adding, that you're mixing, the same on each side or not? If it's not the same, then you're going to have the respective value of the mass there and also there. Okay, so I hope that was instructive. I hope you guys were able to follow through that. Now, what we want to see now is how we can use these quantities to calculate, to work out a real problem. So again, just to go through, M is for the mass, and it has to be in kgs. C is the specific heat capacity. It's particular for the substance. So different substances will have different values of C. Change in temperature, this can have any unit, but mostly you want to look at what C, the units for C. If the units for C are coming with kelvins, then most likely you want to work with kelvins. If they're coming with degrees Celsius, you want to use with degrees Celsius. But you notice that the change will always be the same. Whether you're in degrees Celsius or you're in kelvins, the difference between two values of temperature will always be the same. And then also, yeah, the same quantities are here. And if we go back to our diagram, LF, this is the latent heat of fusion, and LV is the latent heat of vaporization. Questions will always give you what these values are, so you don't need to memorize them. Okay, let's look at our first question. So let's try to see how we can work out this question. So of course, we're starting with the big ones. So this is a little bit mixed up since we're mixing two things straight away. We're not looking at what's just one liquid or one substance. We'll make this question kind of talks about two things that are mixed together at different temperatures. So let's quickly go to the question. Steam at 100 degrees Celsius is passed into a calorimeter of mass 55 grams, containing 150 grams of a mixture of ice and water until all the ice is just melted. The mass of the calorimeter and its content is then found to be 217.5 grams. How much ice was originally present in the mixture, given all those constant? So we want to find the amount of heat that was the amount of ice that was originally present in the mixture, given that when we added steam, when steam was passed through this calorimeter, all the ice melted, and just after all the ice melted, the mass was found to be this. So quickly notice one thing. If we're to get, so let's just indicate that. So we quickly notice one thing. If we were to determine the mass of the calorimeter plus whatever was inside, we notice that that mass actually becomes 55 plus 150, and this becomes 205 grams. But after the experiment, the mass was found to be, that was 217.5 grams. So we notice a slight increment. So now the question is, where does this extra mass come from? Since, of course, mass has to be conserved here. So where is the extra mass coming from? The only logical explanation is that as the steam was passing through the calorimeter, part of it was being condensed. So part of the steam, which was in gaseous state at 100 degrees Celsius, was being condensed from steam to become liquid. Now, of course, it was being converted from steam to become liquid. And we have to also observe that that liquid actually had to be at 0 degrees Celsius. We'll see exactly how that happens or why it is like that a bit later. So first for now, I want to, okay, so the mass of steam here that actually condensed has to be determined by getting the difference between the two values. And we see that this comes out as 12.5 grams or 0.0125 in kgs. Okay, now that we found the amount of steam that condensed, see, in the mixture or when steam was passed, what was happening is the steam was changed. It's like you had steam which was at 100 degrees Celsius, and then this steam, so this steam, what is happening to it? So we're seeing this steam, first it changes state because it is at 100 degrees Celsius. First, the steam changes state. After changing state, it then drops to 0 degrees Celsius. So let's say this is the point where we have 0 degrees Celsius. Now, during this process, while the steam is being condensed and then losing that extra heat, what is happening the other side? Well, the other side, if I was to draw it somewhere here, the other side, all that is happening is you have the ice. I'm not going to focus on the water part because you had a mixture of ice and water. just want to look at what is happening to the ice. So the ice was actually changing state. So if this is the point 0 degrees Celsius, so this is also 0 degrees Celsius, the ice, during the time the steam was doing all this, the ice was actually changing state. So it was ice at 0 degrees Celsius. It was changing state to become liquid at 0 degrees Celsius. So when the steam reaches this point, when the steam changes from gas to become liquid and then dropping to 0 degrees Celsius, the amount it loses, that's the amount that went to actually convert that ice into liquid state. So in other words, if we say the amount of heat lost during change of state by the steam, and then the amount of heat lost as it reduced to 0 degrees Celsius, this is the heat actually that will be equal to the heat gained by the ice as it changes state from solid to become liquid. So in other words, it's still a classic thing. Heat lost is equal to heat gained. How do we determine this? So of course, this is Q1 plus Q2 is equal to Q3. So Q1, this is this part. So again, remember, there's no change in temperature. So this is MLV, not really LLV. This is ML, but because this has to do with a gas becoming a liquid, it has to do with a gas. So this is vaporization. And then this, of course, is change in temperature. So this is going to be MC change in T. And then here, of course, the ice is just changing from solid, so there's no change in temperature. This is ML, but because this is from solid, that has to be fusion. Okay, so we substitute, we place our formulas. What we have is MLV, and then this is plus MC change in T equal to ML fusion. We just want to distinguish. This is for steam, so I'll put S for steam. And then this is for ice, so I'll put I for ice. Okay, so now when we start working them out, we want to find the mass of ice. So I can divide both sides by LF. So we notice that this becomes MS LVS plus MC SS changing TS divided by LFS, not S now, this is I. This is what is equal to the mass of ice. So notice that we're not talking about that water which was originally present in the mixture, because that was not gaining any heat. The heat was being gained by the ice. It was being lost by the steam. Okay, so from here we're seeing that we can get the mass of the ice by dividing the mass of the steam that condensed, multiplying the latent heat of vaporization of the steam, added to MS CS change in T for the steam, divided by the latent heat of fusion for the ice. So mass is common throughout. I can literally factor it out. So what we have here, I can factor it out and I can perform the substitution. I want to use the kgs, so I'll use that value in kgs. Well, I can just work it out the way it is. That's 0.0125 by 22, that's 70 by 10 to the power 3. This is plus, and then that's 0.0125 by 4.2 times 10 to the power 3. Now the change in temperature, what you guys should take note of is for the steam, temperature changes from 100 to 0. So the change in temperature there is equals to the final temperature 0 minus the initial temperature, that's 100. But we're not really looking at what's what here. All we want to find is what is the change. So we see that the change here is just that whole lot, the 100. So this is what we're going to use. The fact that we're just equating them from here we kind of don't want to look at, okay, the negative when it comes in, because if you want to use the negative, then you have to say Q1 plus Q2 plus Q3 is equals to 0, meaning that there's no heat loss, there's no external heat that is coming into the system. But since we're just equating them here, we just want the change there. So that we just get the 100 there. Okay, so that's 100 we're going to use. This is all divided by the latent heat of fusion of ice. So that is 336 by 10 to the power 6. Okay, so once we've done that, again, notice that for the temperature, I just got that difference. Whether you use it in Kelvins or in degrees Celsius, the difference will still be 100. Okay, so once we've got that, we can now simplify this. So we can perform our simplification. We notice that the mass of ice now becomes 28.4 plus 5.25 divided by 336. So if you perform this calculation, you should see that the mass becomes 1 kg. Okay, so I hope you guys were able to follow through. You guys can try to go through this question, watch it as many times as you can. And then after that, you can try to work out this question. You can try it out, the next question for our video. So you guys can try to work out this question in advance. Okay, so I hope you guys found this video helpful. Otherwise, we'll see you in the next video. This was your tutor.